Hi everyone. Let's start day 2 of this week with Enrico Morgante from Mainz University telling us about relaxium fragmentation. Please.
Okay, thank you. So, the organizer, first of all, for inviting me to present this work. It's a real pleasure for me. So, I'm going to discuss the effect of quantum fluctuations for the relaxion mechanism. And but as you're going to see, what I want to discuss applies as well to, it's not strictly related to the relaxion, but it applies as well to other constructions in which you have, generally speaking, some scalar fields rolling classically down a potential with periodic features. That could be like axion monodromy or this kinetic misalignment / axiogenesis story that people talk about a lot. So, disclaimer, when I talk about the relaxion mechanism, I'm going to assume that let's say the picture of the first paper on the relaxion by the mechanism proposed by Graham, Kaplan, and Rajendran. So I'm going to assume that picture. And in particular, there are a few open problems with that picture that I'm not going to address. So to be clear, there is a cosmological constant problem, which is the fact that you have a potential with many... Okay, no problem. So you have a potential with many minima that are non-degenerate. And you have to be sure somehow that there is at least one minimum which is close enough to 0. And you also have to be sure that your evolution is such that you only populate this one. I don't know how to do it, but I'm not going to address this. And the second thing is an argument that actually, I also don't understand pretty much, so if someone can help me with this later, I would be really grateful. That is the fact that since you have this many minima, the wave function of the universe may end up populating all of them, nevertheless. So it would be very nice if someone can explain me this later. So what I'm going to say is based on this paper, so I'll just leave here the archive reference if you are interested. Okay. So, this said, so my setup is the following. I'm just assuming that I have a scalar field with a potential like this. So I have a linear slope plus some periodic feature which I parameterize like this, cosine of phi over f. Plus maybe some cosmological constant which I'm going to ignore. So essentially this looks like very simple, like this. I'm going to assume that these wiggles, let's call them, are large. That is, so basically this condition means that you have these visible wiggles on top of the slope. This is the first difference with the original, let's say, relaxion proposal, in which you have very small wiggles, and when the wiggles grow, the first time you have v prime equals 0, your relaxion stops here. In my setup, instead, I'm going to assume that you have over these wiggles, you have larger velocity, and you stop due to fragmentation afterwards. Okay.
Excuse me, can you hear me? I just wanted to point out that the microphone is muted, so on Zoom we couldn't hear anything until now. Sorry for interrupting.
Sorry.
No, thanks for telling. Now it should be on. It was in the
now it's on.
Muted. Now it's on.
Yeah, thanks.
The mic was muted, but now it's on.
Okay. Can you hear me now? Okay, good. Should I just continue or should I go back? Okay, just continue. Okay. And so the other thing I'm going to assume is that, so for simplicity, I'm going to take this slope mu and also the Hubble rate equals 0. They don't play any role in what I'm going to discuss. And I can come back to this later. So in the end, for the fragmentation part, these are just like, there is just an upper bound on both these two quantities. And above this upper bound, fragmentation is not efficient. But below this upper bound, you can just neglect them, okay? And the last thing I'm going to neglect, compared to the relaxion, is the growth of these barriers. Of course, I mean, the relaxion, of course, this term here, must be proportional to some power of the Higgs wave, no? Like, in general, I would parameterize this like this, H over V to some power n, then cosine phi over f. So just some scale here. So this is just a parameterization, okay? H is my Higgs wave, V is the value that I measure, so the 246 GV, to some power n, which depends on the model you have in mind. I'm going to neglect this basically for the reason is that otherwise I cannot do the math if I keep also into account the fact that these wiggles grow. We convinced ourselves that this is just an order 1 change in what I'm going to say. But yeah, okay, that's just to give you the rules of the game. Okay. Now, I want to include in this picture the fluctuations of the phi field. So I will expand the phi field like this. Xt equal, I have some zero mode, depends only on time, plus some fluctuations. And I can write the equation of motion for these fluctuations in Fourier space like this. Okay, so at the linear level, this is the equation of motion that I get. And this is the second derivative of the potential computed on the zero mode. Okay. And if you write this explicitly, this is, okay, minus, this is not relevant, and the b to the 4 over f squared. And then you have this cosine of phi over f. Yes, sure.
Oh, let's try. Okay, now it works. Okay, sorry. So this, you're saying mu is equal to 0. That's
Yes.
just for the perturbation, you mean, right? Because not for the zero mode, it's important for...
Yes, of course.
Okay.
So when I study the perturbations, I just neglect V and the Hubble friction. Of course, then, I mean, when you look at the zero mode, you need the slope to get the velocity and Hubble friction and so on. So yes, you're right.
Thank you.
You're welcome. Okay, so this is the equation of motion. So as a first step, I will assume that there is a constant velocity, so that the velocity of the field is constant. So I just neglect the zero mode, the back reaction. So if I assume phi dot equals 0, this thing here is, okay, I get minus lambda b to the 4 over f squared cosine of phi dot constant times t, time, over f. And this is a well-known equation. Is I mean, you just massage it a little bit and you see that this is a Mathieu equation. The Mathieu equation is something well-known, for example, in preheating and stuff like that. And the interesting feature is that it has some parametric resonance. So parametric resonance, I mean that you have some, depending on the value of the parameters of your equation, you may have exponentially growing solutions. And in particular, let me just draw this picture. Lambda b, this is over, no, phi dot squared. And here I have k, so the wave number over phi dot over f. And if this is equal 1/2, you have 1/2 here, 1, and so you have something like this. And inside this region, then there are other instability bands, but they are not relevant for what I'm going to say. So the first one is the only relevant one. Inside this region here, the solution is exponentially growing. So I have phi of k goes as exp of delta k critical times time. And delta k critical, so this is just the width of the band. So the band is characterized by k minus phi dot over 2f, absolute value smaller than lambda b to the 4 over 2f phi dot. And this is what I call k critical, and this is my delta k critical. So this is the position of the band, of the instability band, and this is the bandwidth, okay? Can you see it right here? Yes, okay, very good. Okay, so this is what happens, no? So these fluctuations grow exponentially. Now, just by energy conservation, when you are transferring your energy from the zero mode to these fluctuations, and the zero mode therefore slows down. So like this. So now I allow for some phi dot, yeah, for the second, yeah, situation to be different than zero, be non-zero. Now, so let me draw this picture to make you understand what's going on. So here is your k critical. So this is the instability band initially. Okay, so all the modes at t equals 0, all the modes that are inside this band grow. And just by energy conservation, the velocity of the zero mode decreases. But you see, the position of the instability band is proportional to the velocity. So this goes to the IR. So now the instability band is here. And after some times, this was the initial, let's say, the position of the initial instability band. And then at some point, the instability band is here. And when this happens, this mode stops growing, okay? And I call this time delta t amp for amplification, okay? So this is the time in which you amplify this mode. Okay, now let me, so you can just use this very simple reasoning and this exponential growing behavior to estimate what's going to happen and the equation of motion. Okay, let me skip it now. You can do something more precise, and I'm just going to give you the idea and then the result. So to do things a bit more precisely, you can solve the, so you can analytically solve this equation using, okay, this, you know, energy conservation as well. And here I write, so this is the real part of the Fourier mode. Real imaginary part, I mean, is the same. Here, k, no, sorry, time. So what happens is that initially, this is, okay, let's say this is initially oscillating with some amplitude. Then the mode enters the instability band. You have some exponential growth, like this. And then when it exits the instability band, again, you have some oscillatory behavior. And so here, okay, and then you have some regions in which, like, you have some transition, no? When the modes enters the instability band. And you can solve the equations in these 5 different regions, 1, 2, 3, 4, 5. Here you use a WKB approximation, here as well, and here as well. And in these two regions, WKB doesn't work, but you can approximate the equation of motion and you use some Airy functions. So it's not super complicated, but very tedious. And I mean, it's a very long calculation. But in the end, you use this, you find the exact solution for the growth. So you can find, like, given the initial condition from each single mode, you know what is the amplitude of the mode after it exits the instability band. And then you use energy conservation in this way here, which is just depicted here. And you find the equation of motion for the zero mode. So this is my result. I'm just going to write it here. And you have this very nice, quote unquote, equation of motion. Pi squared f to the 4 over phi dot squared to the -1. So you see, this is the equation of motion. You have phi dot dot, and here you have the velocity at the denominator, second power, and inside the log, and then to the -1. This seems ugly, but actually you can solve it analytically. You can solve it exactly, and you find out the following thing, that is that the evolution, yes, today with the mic.
Yeah. So phi dot is an initial condition. How do you determine? Because it looks like, how are you treating phi dot here?
No. So here is just instantaneous velocity. Okay, yes. So you have to assume some initial condition.
Okay, how is this set up?
Yeah, good question. So, I mean, if you think you are during, so if you are during, okay. So if I imagine relaxing mechanism, no? So I have initially just an initial slope. During inflation, you have like the slow roll solution. So I would just assume that phi dot is that. And then the wiggles start to grow, and this, and you have this, okay.
Wait, so this doesn't asymptote?
Sorry?
This doesn't asymptote the solution to this? I mean, it's sensitive to the initial conditions. That's what. Or does it asymptote to some steady solution?
No. This does not asymptote to a steady solution.
It's not like with usual friction where you get to terminal velocity.
Exactly. No. So you don't have a slow roll solution with this equation. I think so. When we studied this equation, we thought that. So I think that there is some steady. You can find some steady state solution, but only then if you include like the slope and Hubble friction. Okay. So if you include.
So you're treating it as a free parameter?
What? Phi dot.
Phi dot.
Yes. The initial velocity. Yes.
Yeah, I go back to what, but then. So, for example, this violates PQ symmetry initially, right? So, for example,
yes.
So, in order to set it up, in some models, for example, that you mentioned in the beginning, the effective potential, for example, that they were setting up, or they were considering a UV compressor for the axion, for example.
Yes.
It wasn't clear that whatever was generating phi dot was in complete control.
No, I agree with you. So this is like I mean, you need to specify what is the initial phi dot, and that depends on the model you have in mind. So how do you generate this phi dot?
So if you have the slow roll in the original relaxion scenario, is that enough to describe your mechanism?
Yes.
Okay.
No, so, yes. So the thing is, in the original relaxion setup, what happens is, okay, initially you have slow roll. And at some point, these wiggles appear. The only thing that I'm not taking into account here is that these wiggles appear gradually, because I don't know how to do it. So I just assume that they have like instantaneously the final amplitude, okay? This is because I don't know how to treat it otherwise.
I mean, you could do it, wouldn't you be able to do it?
Yes and no. I mean, with realistical parameters, I mean, realistically with, I mean, what you expect for the relaxion, we were not able, let's say. We were not able to do it. And so, yeah, that's all we could do.
I have another question. So,
but, sorry, no, but I mean, we convinced ourselves that this should just be like a order one difference. I mean, once you that the initial velocity is, okay, given, it may be the slow roll velocity, or you have no friction and you just have a free, I don't know, free ball rolling down some potential, some rolling down a slope, and then you get some. I mean, then the velocity when the wiggles appear depends on the field excursion. Okay, I mean, whatever the point is, just the velocity that you have when these wiggles appear. You generate this velocity is another question, which, yeah, we have to address it, but this is independent on how you generate the velocity.
So I have another question. If you have this exponential growth, are you not worried that you will reach the case where delta phi just jumps up the barrier?
Yes. But this was like page 10.
I see, okay.
No, okay. So if you don't mind, I talk about it later.
Sure.
But
sure.
yes, that's yeah. Okay, so just this equation. What happens is that, so given your initial velocity, phi dot 0, in a finite time, the velocity, this is phi dot, and this is time. In a finite time, the velocity goes to 0. Velocity of the 0 mode. And I can compute this. Let me write it. This is I call it delta t fragmentation equals, okay, apart from, there are a lot of factors, phi dot 0 cube over 3 pi lambda b to the 8 log, again, the usual log of 32 pi squared f to the 4 over phi dot squared, yes, phi dot 0. Okay, so here, I mean, this is related to the question. So here is where the initial velocity enters. The initial velocity determines how long do you need to stop the field. And you can write a similar formula. I'm not going to write it, but for the total field excursion. Okay, so it's very similar. You just multiply this by phi dot 0 and some number. Okay, good. Yes, please.
Hi, Enrico.
Yeah.
Can I ask a question? I mean, I'm worried about the point in which phi dot gets to 0. If you look at that equation,
yes,
it seems that phi double dot is singular.
yes.
Right? I assume that you want to claim that now the field stops down. But if I take seriously that differential equation, it seems that the guy is going to start climbing up.
Yes.
So something has to break down.
Yeah.
What?
Okay. Very good. So actually, so I should stop this when the velocity is below the amplitude of this. After that, so to derive this equation, I always assume that the velocity is larger than this. So this works until here. Okay. But after that, I don't really care, because then you are trapped in these wiggles.
Okay, so that's what breaks down. Okay.
No, yes, you're right. No, yeah, I agree. Yes, thanks for the question. Yeah.
Can I then ask? So what happens if that condition that the wiggles are not taller than the slope, and instead there's no minima? Is that nothing happens, or is it going to slow down?
Okay, so very good. So in this equation, in the equation of motion for the fluctuations, the amplitude, so you see, it's only the second derivative, not the first derivative. So in principle, so this exponential growth works the same if you have very small wiggles, because, I mean, this condition only, yeah, I mean, so let's say in the second derivative, the slope does not enter. That's why I said I could just neglect it. The thing is, when you look at the evolution of the 0 mode, in that case, you don't find such a solution.
So what would be the solution then?
Well, in that case, I think you just, so if you have no Hubble friction, the solution is just you keep accelerating. So there is no solution with negative phi dot dot. Under some cases, I think there can be a solution with phi dot dot equals 0. So a steady state or constant
Terminal
velocity. Yes, a terminal velocity, exactly. But I need to think about that. I mean, we did all the study of this equation because so the equation of motion in general with mu and h is much more complicated than this. So you need to do a lot of study limits and so on. So it's a bit complicated. So I think I remember the conclusion was this, that in principle you have this solution. Yes, right.
Okay, thank you.
You're welcome. Okay, so
May I ask another question?
yeah.
I'm here.
Yeah, sure.
So, what about back reaction of the field? So the
Back
homogeneous.
reaction?
So in order to derive that equation of phi double dot.
Yes.
So you've assumed that the motion of the homogeneous part. So I'm trying to understand.
Yes, sorry. You can write the equation of motion for the homogeneous.
So yeah,
part.
what the homogeneous, in other words, the phi homogeneous that you put in the equation of the perturbation. Yeah,
Yes.
is it sensitive to the growth of how are you deriving this?
Yes. So the thing is, what is it? Yeah. So you can write. So when I wrote the equation for the for the fluctuations, you can also this is just a picture, a sketch of what is happening. You can write the equation of motion for the zero mode, which looks like this. So phi dot dot plus, okay, here you add double friction if you want, and the potential. Yeah, okay, let me write it just from this. Plus B prime plus, so this is the back reaction term. You have 1/2 third derivative d3x over the volume. And this is delta phi of x squared. Yeah, okay, equals 0. Okay, so this is the equation of motion for the zero mode. Yeah, I mean, you can do, so you can do either you compute the fluctuation and you plug this into this equation, or you use energy conservation. It's the same. You get that equation anyway. Well, of course, neglecting this. If you don't neglect this, you get some. You can do two things. You add this only for the zero mode, and you have it here, just the same, plus 3h phi dot, etc. If you include double friction also for the fluctuation, then you add some other stuff. It's much more complicated, okay? Just the way it looks, it's more complicated, let's say. Okay, other questions? Okay. Okay, so, yeah, so basically this is this is it for the dynamics. Before going to the conclusions, to the consequences, let's say, let me also mention that so one could be worried that when these fluctuations become nonlinear, everything is screwed. Okay, so we did a lattice. So in the last paper that you see there, we did we put this equation on a classical lattice, and we found the following interesting thing. That is, okay, let me reuse this. So, okay, this is how the velocity decreases as a function of time. This is the linear evolution that I discussed so far. When you put things on the lattice, you find that a very good agreement initially, up to a time delta t amp, which is, let me remind you, this is the time it takes to amplify the first modes. And until this point, all the modes are small, so the wave functions are all small, and so everything is linear. So until it's linear, you have a good agreement, and then the nonlinear dynamics is much more efficient than the linear one. Okay, so if this is delta T frag, I can call this, well, let me write it here. Delta T fragmentation NL, so nonlinear. I write it as delta T amp plus some Z T. This is a number times F phi dot 0 cube over lambda B to the 8. This is the same factor that you have here, you see, in front of the log. And this number, for the typical parameters that you need for the relaxion, this is, we found on the lattice 2.3, okay? So another one number. And you have to compare with that, with the log and the factors in front. And this is a factor of 10, roughly smaller. Okay, so 10 smaller. Okay. The main reason for this is that at the nonlinear level, you have 2-to-1 scatterings and higher order processes. So, yes.
Can I ask you a rather technical question? So essentially, when you discretize a classical field on a lattice, you have a huge danger of not conserving energy because of essentially lattice artifacts. This is quite known. And so one has to do some very special procedure to deal with that. Were you aware of that? Because, I mean, losing energy, your result might seem to point at the fact that maybe you're losing energy because you're discretizing your equations. It's a very sophisticated, I mean, it's known, but it's a very sophisticated procedure that is done usually. You have to pass to light-cone coordinates and do an implicit scheme. It's
But why? I mean, if you have only a scalar field and you
it
neglect
does not conserve energy. I can show you. I'll show you offline.
But you neglect also Hubble expansion.
Yes, if you just take a classical field and you put it on a lattice and you just do the classical evolution, the way everybody would do it, you know, simply, this badly violates energy.
So maybe
I'll
we
show
can
you
discuss
offline.
Later. But okay, so the thing that makes me a bit more confident about this is the following thing, that so what you can do analytically is to go to the second order in the equation of motion. So, and you can look at what happens to second order fluctuations. And the second order fluctuations are sourced by the first order ones. With P. Okay, so assuming you know this, so you know this at the linear level, you plug the linear result into this equation and you look at what happens to the second order fluctuations, and you get something that matches pretty well with the lattice. So if you, for example, if you look at the energy spectrum, and this is what the initial spectrum that you have, you find you find the first peak at K critical. This is just the first order fluctuations that are sourced at around K critical. And then from this one, I don't have the equation now, I forgot to write it, but the thing is this one predicts a flat spectrum here and at least one peak at 2K critical. So basically is when these two modes are parallel and this is too critical or anti-parallel, and this is the flat thing here. And then, okay, and you do this on the lattice, and you find a perfect agreement here, here, and here. And then you see on the lattice higher peaks that you cannot get with this equation, okay? But let's say that this is the only check that we have of energy conservation and so on. So this makes me quite confident about this result, okay?
But also you can just check it, no?
Yes, yeah, no, exactly, as you say. I mean, one could just take the lattice, compute total energy, and yeah, you're right, you're totally right. I mean, one could just check it, and that should be easy to check. Okay, so if there are no further questions, I go to the consequences. Okay, let me clean a little bit the blackboard. What did I do? Oh, nothing. Nothing too bad. Okay, okay, so far I've never mentioned the Higgs or the relaxion. Okay, so all this is general. So you just need some scalar field with a potential like the one I drew before. Now I just focus on the relaxion. So the original relaxion mechanism proposed by Graham, Kapran, and Rajendran. So just write it, call it GKR. This has with X-dependent barriers and so on. The first consequence is that if you do all this during inflation, as it was done in the original paper, you don't need super strong Hubble friction or a very flat potential to get a small velocity. No? So the thing is, in this, how do you stop the field in this mechanism? You know? This mechanism, you have a very shallow potential, and this doesn't work. Is it working now? Okay. Yeah, okay. So when the wiggles appear, the Hubble friction is strong enough that as soon as the derivative of the potential is 0, you stop. Okay. So basically, you're following some kind of instantaneous slow roll velocity, no? As you go over these wiggles. To do this, you need a very flat potential or a strong Hubble friction. And as a consequence, you need, so this process, since you need a very large field excursion anyway, because here you want the mass of the Higgs here should be of order your cutoff, and here should be close to 0. No? So you always need a very long, very large field excursion, and to travel all this field excursion in a very flat potential, you need a lot of time and a large number of e-folds. No, so typically in this case, you need like a number of e-folds 10 to the many. Okay, up to, I don't know. We tried with the parameter space. You can have up to 10 to the 50 e-folds or even 10 to the 100. I mean, okay. And then you wonder how to actually obtain this. The nice thing about this fragmentation thing in this case is that you can have a much larger velocity. So you don't need such a long time to complete the process. And you can leave with the usual e-fold, let's say 10 to 100 e-folds, okay? So let's say this problem is solved in this scenario, okay? Because you don't need, yes?
related to what Michael was asking. Do you end up in the same? How many vacua do you populate?
No, sorry.
How many vacua do you populate in that case?
Okay, yeah, a good question. So, okay, no, yeah, I wanted to say that later. The thing is, you have to be careful, exactly, not to populate more than one vacuum. The thing is, fragmentation by itself, you expect, so the typical fluctuation is of order slightly smaller than this periodicity. It's a non-trivial question to understand what is the probability of having, like, of jumping to the next minimum. Okay, so but it's not. So for sure you don't need like huge fluctuations. So it's not that you have typical fluctuation of order, I don't know, thousands, the period of this field, but order one, order smaller. Huh? I mean that typically.
Sorry, I don't understand.
I mean that typically you have in the end delta phi smaller than 2 pi f.
Oh, so you're saying you only populate one vacuum?
Yes, 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 exactly. I say I'm populating only one vacuum.
No, but do you say that based on the lattice calculation?
Yes, yes. The lattice calculation, you only, I mean, it's, so lattice calculation, you do, yeah, this is what you get, but on a small scale. On larger scale, you have to, I mean, to do some, try to, yeah, to get some analytic argument, but in the end, this is what we.
No, but because,
yes.
But if delta phi is of order 2 pi f, right?
Yeah.
That means that you can without any barrier basically jump from with a very small barrier you can jump from one to the other. And then I don't understand why it doesn't keep constantly happening, as Mina said. That you understand what I'm saying? Like if you, this is very close to the barrier, so wouldn't you just, and this is like the entire perturbation being very close to the barrier, so it seems like you can hop very easily.
Yes, I agree. So the thing is, you cannot. Okay. So what you can see on the lattice is that this is like smaller than, I don't know, okay, a factor like this, no? So you have some factor 1 or 1 to 10, 2, 3, I don't know, smaller than this for the typical fluctuations. And what we could see on the lattice was that for larger fluctuations, so you have some exponential suppression for larger fluctuations, okay? So, but yeah, I mean, you have to be a bit careful also with the lattice, no? So there's only so much that you can do on the lattice. So, but okay, so this is one thing. What should I do now? Should I go directly to this? No, let me finish this and then I try to come back to this now.
Do you think you can finish in order 5 minutes?
Yes. Okay. So just to recapitulate. So in this case, okay, during inflation, you don't need 10 to the many e-folds, but just usual 10, 100 e-folds. And this is already something nice. And in that case, okay, let me just add it here, that, well, you expect rather slow, rather small scale inflation, where the energy scale of inflation is just above the cutoff of this theory. And the cutoff, you push it up to, I don't know, to 100 TeV or few hundreds TeV, between 100 TeV and, I don't know, 500 or something.
I mean, that doesn't need to be inflation, no?
Sorry?
I mean, if you have 10 e-folds, it doesn't need to be inflation. It can be a period vacuum energy domination, but not the original inflation.
Exactly. So yeah. Yes. So the other thing is, yeah. Okay. So since you don't need a strong arbor friction, in principle, at least, you can do this after inflation, Okay. So during radiation dominance, even though in this case you have to think a bit more carefully about the initial condition, of course. You don't need the strong Hubble friction that inflation gives you. And if you do this, the nice thing, so if you're able to do this, the cutoff of the theory cannot be too high. You push it up to 20 TeV or so. I mean, you may ask, okay, why do you do all this to get to 20 TeV? Fine. But that also means that new physics is not too far away. So it depends on your attitude. The nice thing is that you couple this from inflation and you don't have bounds, for example, on the Hubble rate of inflation. You not necessarily have low scale inflation, even though with a caveat. Yes.
Sorry, how do this model to move to the next talk? Better I ask this question.
Very good. Very good, Mina. Very good.
Very good.
Thanks. We have discussion after. We have discussion
Thank you.
after.
I just realized the question I'm about to ask. It takes a long time to explain.
Okay.
Let's move this to after the second talk.
Offline, please.
Please go ahead, Enrico.
Very quick question. If
Yes.
the answer is long, we discuss it later. What does it set the weak scale? Where is the weak scale here in this game? Okay, so later.
No, okay. Well, the weak scale, that's a simple question. So you know the field excursion that it takes to stop the field. So so the fragmentation starts when the electroweak symmetry breaks and the Higgs develops a wave. So in the relaxion, you have some coupling. Let me write it like this. Yes. No, exactly. Sorry. No, this I said in the beginning. So here, I mean, just to do the math, I take them constant because I don't know how to do the math otherwise.
Okay. So
but yes, the wiggles are X dependent.
Okay. I missed that completely.
So it's just that I cannot do the math otherwise. So I just take them constant and convince myself that this works at least order 1. So when I do the parameter space here, I assumed it's not QCD, it's some other sector. The main reason is that with QCD, you have you have small wiggles because it's all suppressed by, you have up Yukawa, no? So in the end, you have small wiggles. While with some other sector, this can be as large as a few hundred GeV. Okay. So, but that's purely because of this. Okay. But now you have to give me 5 more minutes. Come on. Okay. I'm not gonna write anything. You can do it after inflation in principle. We asked ourselves whether the relaxion can be the inflaton itself, and so you can generate a low roll phase. The price to pay is that you need, in this case, super Planckian field excursions. So you can generate a slow roll phase. Fragmentation, so you have reheating through fragmentation because then these particles decay very efficiently in the standard model. How to do is to generate the perturbations. So, okay. Last thing I want to mention is that there was this other relaxion proposal by Janson Hook and Gustavo Marquez Tavares a few years ago, in which, it worked just the opposite. And the thing is, a key feature of that thing is that you have constant wiggles instead of Higgs dependent ones. And the trigger is particle production. In that case, as you can imagine, fragmentation is a problem because that fragmentation happens independently on the Higgs. So you may end up stopping the evolution at some random position that has nothing to do with the Higgs. And this actually happens. So what they proposed, and actually we followed for some time, is that you can do this after inflation. If you do it after inflation, then you take into fragmentation and some other bound, like from cosmology or super red giant cooling and so on, and this is dead. So you just fractions and it's gone. Inflation is a bit more. Then Tevong has other arguments, so to be dead, but okay, I'll let you ask Tevon about this. And yes, so the last thing that I wanted to mention, what happens with large fluctuations, no? That depends on Filippo. So.
Can you make it in, I don't know, 1-2 minutes?
Yes, 1-2 minutes. So the thing is, the problems with large fluctuations are the following. The Higgs mass, the solution to the hierarchy problem, strictly speaking, is not a problem, because even if you populate another minimum, the variation in the Higgs VEV is tiny. The problem that I see are two. One is that the difference in cosmological constant between one minimum and the next is huge. Okay, so I said I was neglecting the problem of the cosmological constant, but this is something I cannot neglect, because I would have a universe in which, like, every meter, or I don't know, every parsec, you have a negative and huge negative CC and then huge positive CC, and this is something I cannot live with. I just want to avoid this. And the second thing is that if you suppose you two separate causally disconnected patches, Hubble patches, or simply two patches separated by more than C times the amplification time. So the process takes place independently in these two. And the thing is, if these two somehow populate two different minima, and then you expect some kind of domain wall to form. And this can happen, for example, if you are in different Hubble patches. So I would expect at least one domain wall to be present at all times. And if you look at the parameters, this is just enough to overclose the universe. Okay, so just want to avoid this. And so what we could, at least, I mean, so it's hard to study this on the lattice, because the scale you study on the lattice is too small. Extrapolating the lattice result, we think this does not happen. The only source of this is actually the initial condition that are set during inflation. Of course, I'm talking about the case in which this happens after inflation, but you still have this field around during inflation, and you have some scale invariant spectrum. And the thing is, so suppose you have a linear slope here, and then here your barriers appear, Higgs dependent, of course. And the thing is, if you start from some different initial condition, and it's after inflation, you don't have a slow roll attractor, so the velocity you have here is different depending on where you start. And therefore, since this depends on the velocity, so the time or the field excursion it takes to stop changes because of this. And you want this change to be smaller than one period of the potential. You can do the math, and you get some bound on the Hubble during inflation, but this is actually not so strong. I mean, depends on the parameters, but it goes from roughly 10 to the 10 to 10 to the 16 GeV. Okay, so that's just to say that even though with this after inflation thing, you think you may decouple this from inflation completely, in the end you have this bound, even though it's mild. Okay. Now I'm done.
Thank you very much. Is there any? Unless there is one urgent question, then there is time later. Maybe from Zoom. I don't see any, so let's thank Enrico again.